So I take it this is the original question. You didn't on your post or in your work, you didn't include this part. So what I did is since you gave this, and so what I did is I substitute, well, the first term I plugged in, substituted 1. 4 times 1 is 4, minus 3 is 1. And for 5, for particular second term, I plugged in 2. That's 8 minus 3 is 5, and so on and so forth. Okay. So what a proof by mathematical induction says, okay, we're looking at what we have, and now we want to show that this will work for any value of n. So kind of like we're doing kind of like an in and out table, except now we're looking for a summation. We want to add all these up. So what you do, the whole process of this, I don't know if you've watched other videos or looked at other work, you got to make sure it works for the ones we have or for the base case. So I know that the first term, if I'm looking for the very first sum, that's just that number of 1. So let's plug 1 into our summation formula over here, except it's not 3. 2 times 1 minus 1, well, that's going to be 2 minus 1 is 1, and 1 times 1 is 1, which is the first sum. How about for the second sum? Here, let me erase this. So the second sum will be 6, right? So that's n equals 2. So we're going to substitute 2 times 2 times 2 minus 1. Well, that's going to be 2 times 4 minus 1, which is 2 times 3, which, yes, that's 6. So it works for the second sum. Yeah, it probably works for the third sum. Here, let's check it out. So the third sum will be the sum of those three numbers, which is what, 15? So if n equals 3, that's the third sum. 3 times 2 times 3 minus 1, that's 6 minus 1. So that'll be 5 times 3, which is 15. So it works for the first, second, third sum. Will it work for any sum? And that's what induction shows us. Because we could keep going, we could keep generating the next number and test that one, but that's not going to get us anywhere. That'll just be discrete. Maybe at some point, sometime it falls apart. So what we'll do is this process of mathematical induction. And the first thing we want to do is show that it works for the base case. And the base case is, well, n equals 1. So since we know the first sum is 1, and 1, we just kind of did this, 2 times 1 minus 1 is going to be 1 times 1, which is 1. So check, it works for the base case. So we went ahead and did it for the second, the third. So let's suppose it's going to work for any case. So now what we're going to do is we're going to do the k case. And the k case is pretty easy. All you got to do is every place you see an n, you're going to replace it with k. I know it sounds kind of like a lame thing. Why do we want to do this? But this is the setup for the induction step. So equal. See, that's all I'm doing is I'm replacing the k with the n with k's. And then what we want to show, here's the induction step. And this is the recipe you want to follow. Do the base case, the k case. Then the induction step is what we're going to do is we're going to take the old sum. We know the old sum works. And then we want to add in one more term. And that should equal some new sum formula. So, what do I got here? Can I move stuff around? So I know the old sum is n, or k, sorry, because I remember how you replaced n with k times 2k minus 1. Then we're going to add in one more term, and that's going to be where k, so the other way to think about the induction step, it's the k plus 1 case. So the formula to generate these, this sequence is right there, or this series. So we're going to do 4 times, and here I'm going to get fancy and write, instead of writing k, I'm going to write k plus 1, because it's one more step, one more number. Minus 3. let's make that black, equals, and now I'm going to replace the k in the old sum formula with k plus 1. I'll see if I can squeeze that all in. So I'm going to write a k plus 1 here. I'm going to write a k plus 1 here. Okay, I see some cleaning up. So now we just got to do some algebra here. I see here. Let's move this up. Let's move this up. That will all move up. Good. So I see I can multiply, distribute through the 2. So I get 2k plus 2 minus 1 becomes 2k plus 1. And the other one is just k plus 1. So we won't do anything more than that. We could FOIL that out. We could expand it. I was just helping somebody yesterday where the expansion helped them out. So maybe we should. Let's see if we can. We'll do it two ways. I'll show you two ways. Let's FOIL this out. So what is that? 2k squared plus 2k plus 1k is plus 3k plus 1. So we'll leave that alone. And now remember, just like when you're doing trigger identities, verifying trigger identities, we don't want to move things across the equal sign. We just work on one side, each side separately. So on this left side, I'm going to distribute the k through. Here, let me get something that works right here. So that's going to be 2k squared minus k, plus, and I'll distribute the 4 through. 4k plus 4, and then minus 3. Now we'll combine like terms. So I'm seeing a single k squared term. I'm seeing plus 3k, and I'm seeing plus 1. And there's the FOIL thing. So there's the verification. That's the induction step. We showed that the left-hand side equals the right-hand side after we did the setup. Now you don't have to FOIL this out, right? I could have just stopped here on the right, and then on the left-hand side we'll just have to factor that. So 2k and k, and what gives me 1 is 1 and 1, and they're both positive, and that gives me 2k, that gives me 1k, which is 3k. So yeah, I factored, so you see how that verifies there, that's the same there. So you don't have to do either you're going to have to expand it on the right or factor it on the left usually. And there are other kinds of inductions that are not as nice, but for this course and for the exam, it's all you're going to have to do is work with an arithmetic series. Okay, hopefully that helps.